Okay. As per the changed agenda, now I get the chance to introduce Yakov. Yakov is well known to all of you. For those of you who have attended any of those ITF sessions or have been in this industry around with respect to IP networking, Yakov is a well-known name. He's the co-inventor of BGP. He's the co-inventor of MPLS, classless interdomain routing, CIDR, as well as author of many RFCs and several books. Yakov has been a JUNIPER fellow for the last 12 years. And I always envy him because he says he only works 2 days a week. I'm sure he does 5 days worth of work in 2 days. I want to be Yakov when I retire for sure. Prior to JUNIPER, he's been at Cisco. He was at Cisco also as a Cisco fellow for 5 years. One thing about Yakov is that he always speaks his mind. He always speaks, what he feels like. And we've had numerous debates on several different topics with Yakov. But again, he always makes you feel comfortable. I'm a much more junior person compared to Yakov, but I've learned a lot from him, not only working inside Cisco with him, but also working with him when he was at JUNIPER. So please join me in welcoming Yakov for his keynote speech on state management considerations for cloud computing.
Well, I'd like to start my presentation by acknowledging a couple of individuals from AT&T who really helped me a lot to kind of crystallize the ideas that I'm going to show you in these slides. With this in mind, let's go into the presentation. So what exactly are we talking about when we talk about cloud computing service? In a sense, it's a paradigm shift where instead of enterprises having their own hardware and software which they use for their computing service, they're going to move the stuff into the cloud, and at which point the computing services are going to be delivered by the cloud computing service providers. And these cloud computing service providers should be able to deliver anytime, anywhere capabilities for the enterprises. Now, for a service to be successful, clearly it has to have a very good technology. And this is the conference about technologies. But let's keep in mind that for any service to be successful, it also has to build on a very solid foundation, economic foundation. So let's spend a couple of minutes talking about what's the economic foundation of cloud computing service. What is the value that this service brings, both to the customer of that service, to enterprises, as well as to the providers of that service? So what's the value proposition for those who are going to buy that service? Well, the idea is actually very simple. The promise is to lower the cost of computing service. How? Well, what you do here is an enterprise is going to shift resources that it would use for its computing service to cloud computing service providers. So as it shifts resources, it also shifts the cost of resources from enterprise to the providers. And that applies both to capital as well as to operational expenses. Well, of course, if all you do is just shift resources from one place to another, there is no value created so far. The magic here comes from the notion of economy of scale, because service providers can lower the cost of that service by taking advantage of the economy of scale and passing some of the resulting savings back to the enterprise, back to the customers who are going to buy that service. And that is where the real value proposition of that service comes into the picture. So it is going to lower, the promise of it is to lower the cost to the enterprises. But keep in mind that there is also a value proposition to the service providers. Because for service providers, cloud computing service represents yet another source of new revenue and potentially new profit. Cloud computing service could be especially attractive to the service provider who offer today 2547 VPN service, because such service providers could bundle cloud computing service with their existing service offering. And there is a great potential to leverage existing business relationship, existing customers. Moreover, service providers could use the existing 2547 VPN or MPLS infrastructure as a way of providing access to cloud computing service. Again, that gives the value proposition to the service providers. And last but not least, remember that service providers themselves can use cloud computing service, so they can use the service for their own internal needs. Now, so you see that there seems to be a value both to those who are going to buy that service and as well for those who are going to provide that service. So there is an economic foundation for the service. With this in mind, let's take a look at what do we need from the infrastructure that would provide such a service. What are the requirements on the infrastructure? Well, as previous speaker mentioned, we should be able to support multiple customers, multiple tenants. And that is commonly known as segmentation. Now, for customers who are going to buy cloud computing service, these customers are not interested in looking at individual physical servers, at individual storage, etc. For them, the service has to be virtualized. So the infrastructure should be capable of abstracting virtualization of the elements that deliver the service. As I mentioned earlier, when I talked about paradigm shift, is the notion of anytime, anywhere delivery of the service. And in this particular context, it means the ability to deliver service fast, on demand. And by fast, we don't mean days or months. We're talking about hours or even minutes. As we talk about infrastructure to deliver this service, we have to be very careful and pay very close attention to both capital and operational expenses required to support this service. Because remember, ultimately, it's all about economics. It's all about money. And last but not least is the infrastructure should be able to support a very large number of customers. Why? Because if you look at the previous slide, I mentioned that the whole value proposition of that service is predicated on the assumption of the service providers to take advantage of the economy of scale. And the economy of scale works only if you have a large number of customers, if you have large scale. Now, let's look now a little bit deeper at one particular aspect of the infrastructure, and specifically at the state management for cloud computing service. Well, because you have a very large number of customers, because the service would need to support a very large number of customers, there would be a very large amount of state to manage. And by state, I'm talking about state associated with individual virtual machines. In addition to that, the state itself could be fairly dynamic. And that is driven by two factors. First is this notion of on-demand, rapid provisioning service. And that means that virtual machines could be created or destroyed in a relatively short period of time. Again, we're talking about hours and minutes, not days or months. And there is another factor that makes the state dynamic. And that has to do with the need to optimize resources, where a service provider who delivers cloud computing service may want to pack as many virtual machines on a server as possible. And this way, to avoid servers being half-utilized. And as servers become idles, the service provider could just turn these servers off, thus consuming the resources required by the cloud computing service. So the bottom line you have to get from that slide is there is a very important aspect of the technology that will be used for cloud computing service, and that is scalability. And scalability here, we talk about two dimensions. both in terms of the total amount of state that cloud computing service has to deal with, as well as dynamics of that state. So now let's talk about what kind of building blocks can we use to handle state management. Well, the first building block that I want to introduce is a donut. So let's talk about donuts. Well, I should apologize for picking up American variety of donuts from Dunkin' Donuts. That wasn't the intention. And of course, I'm not going to talk about Dunkin' Donuts here at all. But the idea of a donut actually is extremely powerful, and you'll see in a moment why. The donut I'm going to talk about is a virtualization donut. So let's take a look at it. At the outer edge of this donut, you have virtual machines hanging around. And you may notice that I have different colors for different virtual machines, because each color identifies a particular customer, a particular tenant. Now, at the inner virtualization edge of the donut, you have what is known as network virtualization edge devices. In IETF terminology, they call them NVEs. And these NVEs use some sort of a tunnel encapsulation to cross both intra-data center and inter-data center network. Now, you may think that what I described to you is something brand new, completely new ideas. Well, I'm really sorry to disappoint you, because the only thing new in this case is the donut and terminology. And to show you why, I want to show you a slide from 1999 conference, 14 years ago. Well, this overlay idea that I showed you in the previous slide actually is very old. It's 2547 VPN one more time. And you know, it's very successful technology, had been widely deployed. And if you think actually about how to map this picture into what I showed you in the previous slide, well, you may think about VMs as hosts in individual VPN sites. You may think of PEs as being network virtualization edge. You may think about a SP router as being intra-data center and inter-data center network. And so PEs form an overlay over the infrastructure of P routers. If you look at where state associated with VPN service is maintained, it's localized to PEs. You know that P routers maintain no VPN-related states. So as you see, look, there is nothing new here. We've been using this technology for a very long time. So going back to the donut discussion, what is important to keep in mind is that everything that has to do with service creation, cloud computing service creation, is fully contained in the donut itself, which means also that the state maintenance management used by the service is also localized to the donut. That is what's important about the donut model. So now let's look at what's in the donut itself. And as you'll see in a moment, there are certain things that have to be in the donut all the time, and there are other things which may or may not be in the donut. Well, what has to be in the donut, what is non-negotiable, is the servers. Why? Because remember, at the outer edge of a donut, you have virtual machines. And because virtual machines reside on the servers, you have to place servers in the donut. Well, is anything else has to be in the donut? Well, the next question you should ask, what about top-of-rack switches? Are they in or out of the donut? It's a very good question. And the answer to this question depends on where you're going to place the network virtualization edge, NVE. And there are two models to that. One is called SIG donut, and one is called SYN donut. Well, in the SIG donut, top-of-rack switches are in the donut for a very simple reason, because in a SIG donut, network virtualization edge is placed on the top-of-rack switches. And therefore, by definition, top-of-rack switches have to be in the donut. In contrast to this, in a SYN donut, as you see, network virtualization edge is placed not on top-of-rack switches, but on the servers themselves. And again, by definition, that takes top-of-rack switches out of the donut immediately. So these are the two models that we have to keep in mind. And now let's compare and contrast the two. So let's start with thick donut. Well, if you look at the thick donut and you think about service creation management, then you should be able to realize that it does require certain coordination between servers and top-of-rack switches. Why? Because NVEs is actually located on the top of rack, and VMs are located on the server. And this coordination could be done either via some sort of a protocol or via orchestration provisioning system. Either way, it does add complexity to the system. And the question you may ask is, well, what's the value in that complexity? It's a very good question. Well, there is an expression that the best way to solve the problem is not to have it in the first place, and it's applicable here really well, because the best way to answer this question of extra cost is just not to have it. How? Well, let's just move NVE from a server, from a top of rack to the server. From that point on, you don't have to have any issue of coordination between the server and the top of rack, because NVE is on the server itself. And so as a consequence of it, one implication of the thin donut is that it gives us overall simpler picture than the thick donut. That is not the only benefit of the thin donut. Now let's look at another aspect of the donuts. Well, look at top of rack 3, TOR 3 switch, and NV located on that switch. If you look at think about amount of state that this top of rack switch has to maintain, this NV has to maintain. It has to maintain state for red, purple, green, and yellow customers. In a sense, it has to maintain state for all the customers that reside on the servers connected to the top of rack switch. Now let's compare it against the thin donut. Well, look at NVE located on the server 5. Well, in this case, NVE has to maintain state only for red and blue customers, but not for green and yellow. And if you look at NVE located on server 4, you'll notice that this NVE has to maintain state for green and yellow, but not for red and blue. So as a result, you'll see that thin donut has better scaling properties in terms of the amount of state that individual NVEs have to maintain relative to the thick donut. And by the way, improving scalability in terms of state has implication not just the amount of memory required by the NVE, but also in terms of CPU resources, because state maintenance does involve computation. There are other benefits of the thin donut. If you move NVE from top of rack switches to the servers, you should be able to realize that the aggregate data rate that an NVE has to handle is lower, for a very simple reason. Because if NVE is located on the top of rack switch, then the aggregate data rate that NVE has to handle is determined by all the servers connected to the top of rack switch. On the other hand, if you have NVE located on a server, then the aggregate data rate that NVE has to handle is just the data rate that is driven by that server and no other servers at all. And that, in turn, allows us to implement most of the functionality required by NVE in the software. Why is that important? Well, it is important because it allows us to unbundle, to decouple functionality you need for cloud computing service from capabilities of the hardware you use to deliver the service. Why is that important? Well, because as you unbundle this, you also reduce or eliminate altogether hardware dependencies imposed by cloud computing service on the service creation points on NVEs. And that, in turn, has the promise, and I want to stress out, at this point in time, it's just a promise, to lower the cost of the infrastructure that you need for cloud computing service. There are other benefits of the thin donut, and specifically the ability to implement functionality in a software. By unbundling functionality required for cloud computing service from the hardware capabilities, and by implementing most of its functionality in a software, it allows us to have more rapid deployment of new features and services, because you no longer depend on specialized hardware, and you no longer need to revalidate software on newer versions of hardware. And likewise, it gives us more flexibility, because if we want to implement new features and services, we just depend on the software. We have very little, if no dependencies, on the hardware. Well, of course, we know that there is no such thing as free lunch. And what I described to you is yet another illustration of this paradigm. Why? Well, because NVE, implementing NVE, does require resources. There is no magic here. And if you look at the thick donut, these resources are taken from the Tor. Implementing NVE on the Tor doesn't take any resources from the servers. In contrast to this, if you're going to place NVE on a server, at that point, you're going to use server resources to implement NVE functionality. And you can say, well, the server actually should use its resources for virtual machines, not for NVEs. Yes, there is no such thing as free lunch. So yes, the argument could be made that by placing NVE on a server, you do take away resources that otherwise could be used by virtual machines. It's a true statement. However, let's also keep in mind that servers are getting more powerful. That is just a fact of life. And also the cost of computing on servers is also getting down. So yes, there is a trade-off involved between thin and a thick donut. And I just presented to you all the trade-offs. It's up to you to make a judgment. The next question you may ask me, well, can I actually build the service just relying on a thin donut? Is thin donut enough? Well, the thin donut is like a goal, but let's just be practical. There may be cases where thin donut may not be enough. So let's look at a couple of them. For one thing, in your infrastructure, you may have servers that just don't support virtualization. For whatever reason, it really doesn't matter, but they do not. Well, if a server doesn't support virtualization, then, well, you cannot implement NVE functionality on such a server. And the only option you have at this point is to place NVE on a Tor. So in a sense, you do insert a wedge of a thick donut into otherwise a pretty thin donut. Well, let's just be pragmatic about it. There is another case where you may deviate from this ideal of a thin donut, and that is when you want to interconnect cloud computing service with 2547 VPN, where in effect, actually, you have to deploy somewhere what amounts to a PE. And yes, you can collocate NVE and VRF on the same router, but again, by adding router to the picture, we effectively deviate from this notion of a thin donut. Well, are there any other options to interconnect 2547 service with cloud computing service? I don't know. But look, again, let's keep in mind that we just have to be very pragmatic. And thin donut is an ideal situation, and we may have less than ideal solution in practice. I want now to talk a little bit about centralized and distributed state management. And as you'll see, I put centralized versus distributed state management here. And I put versus in parentheses. And you'll see in a moment why. Well, if I just want to talk about centralized versus distributed state management, I could probably take the rest of this day and, in fact, the rest of the conference, because there have been plenty of books written, plenty of doctoral dissertations written on this topic. I am not going to do that. I want to frame it in a very specific context, and that is, I want to talk about centralized versus distributed state management in a context of the cloud computing service. And just to remind you, what's important about that service is you have a large amount of state, and the state itself is fairly dynamic. And therefore, scalability, both in terms of the total amount of state and in terms of the state dynamic, is very important. Well, let's start with centralized state management. Well, one of the obvious problems with centralized state management is that it's going to create a single choke point. And so if you think that large-scale cloud computing service could be managed using centralized state management, you're clearly wrong. It just wouldn't scale. And the folks actually who are proposing centralized state management, they're by no means stupid, and they understand it really well. And that's why they came up with this concept of, quote, logically centralized and physically distributed. And if you think about it, it's an implicit acknowledgement that truly centralized state management just doesn't work in that environment. Well, once you have it physically distributed, then the question you should ask, OK, well, you have those different boxes. How do they talk to each other? Aren't they need some kind of a protocol? The answer is probably yes. Do we have existing standards for this? Well, I don't know. It's a good question to ask. But to me, this whole discussion of logically centralized and physically distributed is just nothing but smoke and mirrors. Look, if it's physically distributed, it is distributed. So let's just talk about distributed state management. And in this case, what you have is state management is handled by multiple entities. It's as simple as that. Now, to understand how centralized and distributed state management could be used in the context of cloud computing service, we have to decompose the state associated with cloud computing service into 3 categories. There is, when you create a virtual machine on a server, there is a state associated with that virtual machine on that server. But also, VMs, virtual machines, don't exist in isolation. They talk to each other. So as you create a virtual machine on a given server, there are other virtual machines that talk to that VM on other servers. And other servers have to have state for this newly created virtual machine. And moreover, as you create virtual machine on a server, this server also has to have state for other VMs with which the local VM talks with. And now that brings me to the point about centralized and distributed state management. You know this expression, everything is good in moderation. And this is no exception to that. For managing state associated with the given VM on the server hosting that VM, centralized state management is just fine. It's a very good match. And it could be done by a provisioning orchestration system. And remember, just because centralized state management isn't suitable for manage all sorts of states in cloud computing service doesn't mean that it's not suitable for one particular type of state. It is suitable really well. And for other 2 categories of state, we should rely on the distributed state management. So the next question you may ask is, well, so what kind of tool we're going to use for distributed state management? Well, the tool I'm going to use is described on the napkins. And you may not see that really well because it's a very small print. The napkins are fairly old. But there is something in the upper left corner of the napkin there. And if you cannot read there, I can read it for you. 3 letters there. B as in boy, G as in George, P as in Peter, which stands for BGP. And on 3 napkins, what you see here is actually the first version of BGP. And of course, what I'm going to describe you next is how BGP could be a very suitable candidate for distributed state management. Well, there are well-established techniques for large-scale state management. And I'm going to just talk about a couple of them. The first one is hierarchy. So what is hierarchy? It's all about? Well, with state management hierarchy, what brings to the table, it eliminates the need to have full mesh control peering between all of the endpoints. What is also important, though, about hierarchy is that eliminating full mesh peering in a control plane shouldn't force corresponding hierarchy in the data plane. That is, you may have hierarchy in the control plane, but this hierarchy should not be imposed in the data plane. So let's see how can we accomplish this with BGP. Well, BGP has a well-known concept of a route reflector. So to avoid full mesh peering among all the endpoints, we have route reflectors, because in this case, a state management endpoint doesn't have to peer with all other endpoints. It could peer just with a couple of route reflectors. In terms of not forcing control plane hierarchy on the data plane, again, BGP has a well-known mechanism to accomplish that, which is known as third-party next hop. And that's precisely what allows us to bypass route reflectors in the data plane while making route reflectors essential part of the control plane. And of course, if one level of hierarchy is not enough, you can add extra layers by forming hierarchy of route reflectors. These are well-established mechanisms. There is another technique that, again, had been known for quite a while, known as divide and conquer. And applying it in the context of cloud computing service, what that really means is that a given NVE should not be required to maintain state for all the VMs in the whole network. It should be required to maintain state only for VMs of a particular tenants who have VMs hosted on that NVE. Well, again, how can we accomplish this with BGP? Well, BGP has, again, a well-established mechanism to do it, known as route target and route target constraints. And what this mechanism allows us to do, it allows an NVE to use route target constraints to inform route reflectors of the customers that this NVE is interested in. And as a result, the route reflector is going to give to that NVE only the state information of these customers. Of course, the divide and conquer and the hierarchy are not mutually exclusive. You can combine them together, because you can use BGP route reflectors and you can use BGP route target constraints together. As a result of doing it, you'll end up in a situation where no single element in a system has to keep state for all the virtual machines in the system. And as a result, the overall capacity of the system is no longer bounded by capacities of its individual components. There are other benefits of using BGP, because BGP as a protocol, as it evolves from its early days, from its 3 napkins, right now can carry all sorts of state information. And what I put here on this slide is by no means an exhaustive list. What is also important that what I put on that slide are either IETF standards or on IETF standards track. And whatever I put on this slide is actually applicable and relevant when we talk about state management for cloud computing service. So what's good about it is that you have a single tool that can deal with distributing a variety of state information. Well, we've seen this movie before, and that is there are some misconceptions about BGP. And when we talk about bringing BGP and using BGP for cloud computing service, this is not the first time we've seen this misconception. We've seen them before. We've seen them at that conference. And most misconceptions have to do with confusing implementations of a particular technology with technology itself. And just to illustrate this point, I picked up here a couple of quotes from the presentation that was made last summer at the Cloud Computing Service here in Paris. Well, the first quote is that 2547 VPN virtualizes forwarding table only. Well, if you just know even a little bit about 2547 VPNs, you should be able to realize that this is a completely bogus claim. because it certainly does virtualize forwarding state, but it also could virtualize a whole bunch of other state, like routing information, flow spec, and so on and so forth. Another claim which I picked for this slide is this claim that 2547 VPN don't support rapid provisioning, less than a minute. You know, that is a true statement. However, it is true with respect to 2547 implementations. And moreover, it is true with respect to, I would call legacy 2547 VPN implementations, because you'll see now new implementations coming in that allow very rapid provisioning of VRFs. So the point to keep in mind that, yes, there are limitations on the implementations of various technologies, but let's not confuse these limitations with the technologies themselves. And that, of course, brings me to the next question. Do we have existing mechanisms and tools for cloud computing service? Or do we need yet another control plane protocol? Well, look, we don't. We already have enough. We may need to fix our implementations. But in terms of technologies, we have existing mechanisms and tools. They may require some minor extensions, but that's certainly not yet another control plane protocol. And here I'm talking about two particular technologies. It's either 2547 VPN or EVPN. And what is also attractive about both of these technologies is that they do facilitate seamless integration between cloud computing service and 2547 service. And also because these technologies are kind of, EVPN is pretty much very similar to 2547 VPN, and service providers have very extensive experience with 2547 VPN, it could lower the operational cost to the service providers because it reduces the learning curve for them. And that brings me to the last part of my presentation. So the cloud computing service has to be built around the notion of the thin virtualization donut. But as I said, let's not be dogmatic. And thin virtualization donut is a nice goal. But in reality, we may insert thick wedges here and there just to satisfy some practical considerations. There is a great value in implementing NVE in software. And it's very important as we go into cloud computing service. The discussion about distributed and centralized should not be one versus another. It should be about judicious combination of both. Each has its own role. Let's not deny it. And the last point I want to make is that for distributed state management, we do have existing protocol. We don't need yet another one. And that is the end of my presentation. Thank you very much.
Any questions for Yakov, ladies and gentlemen? Well, we've heard BGP is the answer. What is the question? Come on. But kidding aside, this is yet another interesting use and application of BGP. So, no questions? Thank you very much, Yakov. Appreciate your time. Give me one.